This is the title of our group, which is the application of line integral on spiral structures. Okay, first, let's begin with the basic introduction to the line integrals. When we first learned about the integration in calculus, it usually involves single variable function, but in real-world application, especially in physics and engineering, we often deal with motion and forces in 2 or 3 dimensions. Line integral extend the idea of definite integrals from straight line to curved path. Instead of integrating over an interval, we integrate along a curve, which is especially useful when dealing with the vector field like force, velocity, or electric field. Next, for the scalar function, where we integrate function like fxy over a curve in xy plane, the formula of the line integral involves the function and the arc length of element. In 2-dimensional, the line integral becomes area equal to integrate fxt yt square root dx dt squared plus dy dt squared dt. And in 3-dimensional, we just include the z component, which is area equal to fxt yt zt square root dx dt squared plus dy dt squared plus dz dt squared. This formula calculates the accumulative value of the function along the path, not just across x or y values. Okay, then let's move on to the line integral over vector field. This type of integral is commonly used to calculate the work done by a force field along a path. Mathematically, it's written as integrate f dot dr, or more specifically, in terms of component, it becomes integrate f dot dr equal to p dx plus q dy plus r dz. If the curve C is parameterized as the vector function rt, where t goes from a to b, the formula becomes integrate upper boundary b lower boundary a frt dot r prime t dt. This represents the dot product of the force vector and the velocity vector at the very point on the path.
Okay, today I would like to explain about work as line integral. The work is influenced by a continuous force field F equals to PQR on a particle that moving along a smooth curve C. The formula to calculate the work is W equals to integral F dr, which is same as integral P dx plus Q dy plus R dz. The curve C must be smooth and oriented in the direction of motion. Next, to compute the line integral, we need the parametric equation of the curve. Okay, next, to compute the line integral, we must express the curve C using a parameter. Usually, we call it as t, and as you can see in the table, there are some of the common curve that we use. The first one is ellipse, which is it have 2 types of parametric equation, which is counterclockwise and clockwise motion. The second one is circle. It also have 2 types of parametric equation, which is counterclockwise and clockwise motion. For the third one is for the functions like y equals to fx, we can simplify it by letting x equals to t and y equals to ft. And lastly, for the line segment, from one point to another in 3D space, we can use the formula which is rt equals to 1 minus t x naught y naught z naught plus t x1 y1 z1, where t goes from 0 to 1. Okay, this parametric equation could help us to transform the line integral into a standard definite integral with respect to t, which we can then evaluate the formulation easily.
So, here is the question from our first case study. In a modern water filtration plant, water flows through a vertically rising spiral pipe. To analyze the work required to move a particle of water along the spiral pipe, engineers model the motion of a water particle using the spiral path, which is rt equal to cos t sin t and t for when t is between 0 and 2 pi. The force field applied by the pump that pushes the water along the spiral path is modeled as Fxyz equal to negative y, x, and 2z. Determine the total work done by the force field F in moving a single water particle along the spiral path RT. To do this, compute the line integral W equal to integration of f dot dr, where c is the path described by RT. Next, I will explain the manual calculation for first case study, which is the first step is we need to identify the force field and the path of RT, where we identify that the force field is negative y, x, and 2z, and RT equal to cos t, sin t, and t for when t is from 0 to 2 pi. Next, we determine the result of dot product calculation between FRT and derivative of R. So what we need to do is to substitute RT into F, then we will get negative sin t, cos t, and 2t. After that, we differentiate R with respect to t. Then apply the dot product of FRT and dr, where we will get 1 plus 2t dt. And the last step, we will find the work done by integrating the result obtained from dot product of FRT and dr. Then, we will get 2 pi plus 4 pi the power of 2. Therefore, the total work done is 2 pi plus 4 pi the power of 2.
Okay, then let's move on to the maple solver. The first question. The first step, we need to define the spiral path. This defines the position vector RT, which describes the three-dimensional spiral path. X equal to cos t, y equal to sin t, z equal to t. The particle move from t equal to 0 and to t equal to 2 pi. Then we compute the derivative of RT. This gives the r prime t, which is the velocity vector, which is the rate of change of position with respect to time. After that, we define the force field F. This models the force field as a vector function dependent on x, y, z, with x component equal to negative y component equal to x, and z component equal to 2z. The first step, we need to substitute the path into the force field. This replaces x equal to cos t, y equal to sin t, and z equal to t for giving FRT. The fifth step, we need to compute the dot product of FRT and r prime t. This calculates the dot product f dot dr dt at each point t. We need to integrate to find the total work. This compute the line integral over the spiral path to get the total work done by force field. After that, we evaluate the function numerically by using evolve. And lastly, we plot the three-dimensional spiral path by using width plot function. This generate the three-dimensional plot of the spiral curve matching with the path defined by RT.
Okay, next, this is our case study 2. A decorative LED light strip is installed along a spiral staircase railing in a luxury hotel. The railing follows the 3D spiral path with RT has been given, and the brightness needed per unit length depends on height and given by F, X, Y, Z is equal to 10 plus X lumen per amp. By evaluating the line integral to compute the total brightness output required for the entire LED installation along the staircase. Next, I will tell on how to solve the case study 2. The question is required to compute the total brightness output required for the entire LED installation along the staircase. Firstly, we must know the formula, so we will use line integral over scalar function. So the formula is integrate fxt, yt, zt and multiply it with square root of dx over dt power of 2 plus dy over dt power of 2 plus dz over dt power of 2 dt. But we can simplify it to norm of r prime t dt. Then we can start find the answer. Step 1, we need to find f, x, y, z and rt. But our question already given to us, which are f, x, y, z equal to 10 plus z and rt is cos t, sin t and 0.t. Step 2, we make a parametric equation xt equal to cos t, yt equal to sin t and zt equal to 0.3t. And step 3 is to find the r prime t, and we will get x prime t equal to negative sin t, y prime t equal to cos t and z prime t equal to 0. We continue from the previous video to step 4, which is calculate the ds by finding the norm of r prime t. Then we will get the answer square root of 1.09 dt. t. Lastly, we will move to the step 5, which is solve the integral tan plus z ds. By fill in all the information we get in step 1 until step 4. Then we will get the answer 202.64 lumens.
Okay, I will explain about the maple solver for the question 2. First of all, we need to define the position vector RT, which consists of x, y, and z components. Next, we need to find the derivative of RT, which is r prime t, and this is used to calculate the arc length ds. Then, we use the evolve and square root function to get the dst, which give the distance moved along the spiral. Then, we need to define the brightness function bt, and which means the brightness increased with the time. Next, the total brightness along the spiral is calculated by integrating bt multiply ds from t0 until 0.5 pi. Finally, we will get the output, which is the total brightness is equal to 202.6. Okay, next, for a better visualization, we use the Pascal function in Maple to plot the spiral. First of all, we need to load the plot package by using the command waveplots. Then, we need to define the parametric equation, and after that, we use a 3D plot. As shown in the 3D plot, the spiral wraps around the z-axis while moving upward. This could help us to understand the shape of the path where we calculate the brightness.